By now, we've seen how calculus can solve a wide variety of interesting and useful problems. But there's a burning question we've been ignoring this whole time. Why does it work? Take a moment to think about just how much we've accomplished up to this point. We've developed two essential tools: the derivative, which is the slope at any point of a curve, and the integral, which is the signed area between a curve and the horizontal axis. We've seen that there's a deep fundamental relationship between these two tools, that in a sense, derivatives and integrals are opposites of each other. And we've seen how derivatives and integrals can be used to solve a whole host of problems in every field of study imaginable. It's no wonder that calculus is often considered one of the greatest mathematical achievements of humans. But you may have noticed that a lot of our results rely on a concept that doesn't usually get explored much in math class: infinity. Which is kind of a shame, because infinity is without a doubt one of my favorite concepts in all of mathematics. Both the derivative and the integral invoke ideas of infinity. To get the derivative, we imagined finding the slope between 2 points that were infinitely close together, a ratio of 2 infinitesimal changes. And to get the integral, we imagined splitting up a region into a smooth sum of infinitely many rectangles, each one with an infinitesimal width. These intuitions give us a vivid mental picture, but the problem is, it's difficult to pin down just what it means to be infinitely close or infinitely thin. In fact, infinity has been a controversial topic in mathematics for a very long time, and mathematicians have long debated just what its role in mathematics should be, especially when it comes to the idea of infinitesimal, that is, infinitely small, quantities. So, let's talk for just a moment about the story of calculus. You may have heard by now that calculus was independently invented by Isaac Newton and Gottfried Leibniz. There's actually a lot of controversy over who should get credit. Newton claimed to have come up with the idea first, but Leibniz was the first to publish. What many people don't realize, though, is that the ideas of calculus predate the both of them by as much as 2,000 years. The ancient Greeks, for example, tackled the questions of both tangent lines and curved areas, making heavy use of infinitesimal ideas, what they called the method of exhaustion. Since then, many other mathematicians added on little bits of insight. And it wasn't just Europeans, by the way. China, India, and the Middle East had many mathematicians who investigated the central ideas of calculus, and they definitely deserve way more credit than they usually get. So it's not quite right to say that Newton and Leibniz invented calculus. What they did do, though, is bring many of the ideas of their predecessors together into a cohesive body of study, and recognize the deep fundamental relationship between derivatives and integrals. Also, Leibniz's notation had a slight edge. He's the reason we use D for small changes and a long S for a smooth summation. You don't see Newton's notation used all that much anymore, except in special cases. Both Newton and Leibniz made use of infinitesimals in their development of calculus, but they were very informal about it. It was all kind of ad hoc, and that made a lot of mathematicians in the years ahead very uncomfortable. Everybody started using calculus, and nobody could deny that it gave the right answers to a lot of hard problems, but nobody could explain why it worked. Eventually, people realized that this was becoming a problem. And so mathematicians set out to nail down exactly what was going on, to try to formalize calculus and give it a firm logical footing. And that is what gave rise to the main concept of this video, the idea of limits. I don't know where I'd be without music. I usually listen to music when I'm studying or planning or grading or even working on videos. In fact, studies have shown that music can help the brain with motivation, focus, and even memorization. Though of course, the kind of music matters. That's why when I put music in the backgrounds of these videos, I try to pick music with no lyrics so that it doesn't become distracting, and I try to make sure it's not too loud so it doesn't drown out my voice. Now, you've probably heard that math and music have a lot to do with each other. Obviously, melodies and rhythms have mathematical elements to them, and sound waves can be modeled using sines and cosines. But a particularly interesting question is how sound is stored and then played back. When you open an MP3 file, in order to have it played through your speakers, that digitized sample has to be converted to an analog signal. The question of how to do this is one of many problems studied in the field of digital signal processing, or DSP for short. One of the most important functions used in DSP all over the place is the cardinal sine function, also called the sinc function. The C stands for cardinal. Roughly speaking, the sinc function can be used to pick out a single value, a sample, out of a larger waveform. Algebraically, the sinc function is defined as sine x over x, and its graph has one large peak at x equals 0 and many smaller peaks as we go outward. Now, just how high is that peak in the middle? Well, that's easy. You just plug in 0 and... oh no. If we plug in 0, then we end up dividing by 0. That's usually kind of a problem in math. So sine x over x is undefined at x equals 0. But let's take a different approach. Literally. Suppose instead of plugging in x equals 0 directly, we plugged in something close to 0, say 0.1. If we substitute 0.1 into sine x over x, we get about 0.998334. Neat. Now, what if we plug in something closer, like 0.01? That gives us about 0.999983334. Oh, that's a cool pattern. In fact, I bet you could guess what would happen if we plugged in 0.001. Can you guess? You get about 0.9999998333334. So there's definitely something going on here. Ignoring the cool patterns with the digits for a moment, it seems that as x gets closer to 0, then the value of sine x over x gets closer to 1. The same thing happens if we plug in negative numbers close to 0, by the way, because of the symmetry of the sine function. So we say that 1, the value the function is approaching, is the limit of the function as x approaches 0. Here's how we would write it, and out loud we would read this as the limit as x approaches 0 of the function sine x over x is 1. Notice that we don't say the limit is approaching 1, but rather the limit is 1. You can think of the limit as the intended destination of the function. Now, intuitively, it's really tempting to say that if x were infinitely close to 0, then sine x over x would be infinitely close to 1. But hold up, isn't that the exact same hand-wavy infinitesimal stuff that we're trying to get away from in the first place? Well, it turns out there is actually a precise way to talk about this. When we say that sine x over x gets closer and closer to 1, what we really mean is that it can get as close as we want to 1, what we might sometimes call arbitrarily close. That means you tell me how close the output, the y value, should be to 1, and I can tell you how close the input, the x value, should be to 0. For example, say you wanted to make sure that the output was no more than a millionth away from 1. So it has to be between 0.999999 and 1.000001. Well, turns out that if I make sure that x is between about plus or minus 0.002444949, then the output will never be more than a millionth away from 1. If you gave me a tighter interval around 1, I could find an even tighter interval for x around 0 that makes sure that y stays within that distance of 1. So that's what we mean when we say that the limit of the function is 1. We can get the outputs as close as we want to 1 by picking inputs close enough to 0. Now, we could summarize what we've been saying here in precise mathematical symbols, but to be honest, the notation would get pretty cumbersome. But if you really want to see the precise mathematical definition of what we've been doing, here it is. The infamous epsilon delta definition of a limit. If looking at this gives you insight into how limits work, congratulations. But if looking at this makes your eyes glaze over, don't worry too much about it. It's really just here for completeness' sake, because for some reason a lot of mathematicians are in love with this definition. Anyway, as far as I'm concerned, if you have an intuitive image, a picture in your head of a function getting closer and closer to some value, as close as you want, then you're in good shape. The important thing to understand is that limits give us a precise way to talk about the idea of closeness. We can also use limits to talk about the long-term behavior of a function. For sine x over x, as x gets larger and larger, the denominator gets very large, while the numerator is always stuck between -1 and 1. That causes those peaks to get smaller and smaller, and the function gradually levels off to 0. So we can say that as x approaches infinity, that is, as it grows larger and larger in the positive direction, sine x over x approaches a limit of 0, as close as we want. The same goes for if x goes out to the left. The denominator still grows larger and larger without bound, while the numerator is still stuck between -1 and 1. So here, as x approaches negative infinity, growing larger and larger in the negative direction, the function sine x over x still approaches a limit of 0. By the way, I'd like to take this opportunity to point out something that often gets taught wrong in math classes. Let's bring back a little vocabulary. What's the definition of an asymptote of a function? If you said a line that a function gets close to but never touches, that's actually incorrect. It's true that the distance between a curve and its asymptote does approach 0 as you go further and further out, but there's no rule saying you can't cross an asymptote. Even though there are many curves that don't cross their asymptotes, that's not actually part of the definition. The sinc function has an asymptote of y equals 0, because as you go further out in either direction, the y value approaches 0. But if you plug in any non-zero multiple of pi, say 2 pi, 3 pi, 18 pi, you get 0. So it crosses its asymptote infinitely many times. So if never touches was part of your asymptote definition, you should try to unlearn that. There are many examples of functions where that's just not true. Let's look at another function that's often used in DSP, as well as a number of other applications, the so-called Heaviside step function. It's defined to be 0 when the input is negative, and then 1 when the input is 0 or positive. You can think of it as representing a switch that gets turned on at 0. So how can we use limits to describe what happens to the step function as x approaches 0? Well, if we let x approach 0 from the right-hand side, plugging in smaller and smaller positive numbers, we always get 1. So we can get a little more granular and say that the right-hand limit, which we write with a little plus sign above the 0, is 1. As x approaches 0 from the right side, the function approaches 1. But what if we let x approach 0 from the left-hand side? If we plug in smaller and smaller negative numbers, we always get 0. So we'd say that the left-hand limit, which we write with a little minus sign, is 0. As x approaches 0 from the left, the function approaches 0. Our left-hand limit doesn't match our right-hand limit. That presents a bit of a problem because it means that we can't talk about the limit of the function as x approaches 0 unless we know which direction we're coming from. So here we'd say that the limit does not exist because the one-sided limits don't match up. In contrast, if we go back to sine x over x, then as x approaches 0, the function approaches 1 no matter whether we come from the left or from the right. So the left-hand and right-hand limits are both 1, which means that the limit is also 1. So in order to talk about the limit of a function, both the left-hand and right-hand limits have to match. Otherwise, we say that the limit does not exist. So we know that as x approaches 0, sine x over x approaches the limit of 1. But that doesn't change the fact that we can't directly plug in 0, so the function never actually reaches 1. What we have is an issue with the function's continuity. It's discontinuous at x equals 0, while at any other point it's continuous. You've probably heard of continuous functions before. Usually when you first learn the idea, you might say that a function is continuous if you can draw it without picking up your pencil. So for example, polynomial functions are always continuous, as are many other functions you've learned about. But limits give us a new, more precise way to talk about continuity. We say that f is continuous at a point x equals a if the limit as x approaches a equals the value of the function at x equals a. That means that the left-hand limit, the right-hand limit, and the function value all have to exist, and they all have to match. So for example, if we look at sine x over x, and we look at what happens at, say, x equals pi, then the left-hand limit, the right-hand limit, and the function value are all 0. So that means the function is continuous at x equals pi. On the other hand, if we look at what happens at x equals 0, then the left-hand limit at 0 matches the right-hand limit, but the function is undefined at x equals 0. So sine x over x is discontinuous at x equals 0. Interestingly enough though, most people who use the sinc function get around this issue by simply defining the sinc of 0 to be 1, making the function continuous at x equals 0, and hence continuous everywhere. That's why we call the discontinuity in sine x over x a removable discontinuity. All we have to do is define or redefine the function at that one point, and we can make the function continuous. Now, let's look at the Heaviside step function. Here, the left-hand limit, the right-hand limit, and the function value are all defined. And the right-hand limit does in fact match the function value, but the left-hand limit doesn't match. So once again, the function isn't continuous at x equals 0. This time, there's no saving the function by just redefining a single point. You'll never be able to get rid of that jump in the function. Fittingly, this kind of discontinuity is called a jump discontinuity. There are two other kinds of discontinuity that could come up. A function could have an infinite discontinuity, where one or both branches of a function blow up to infinity, like with the function 1 over x, as x approaches 0. Or a function could have an oscillating discontinuity, where the function oscillates faster and faster, like with the function sine of 1 over x. That last one, by the way, gives another way that a limit can fail to exist. Not even the one-sided limits exist because they never settle down, or converge, on a single value. So the big takeaway here is that limits give us a more precise way to talk about the behavior of functions. Instead of talking about what happens at a particular input value, limits are concerned with what happens around an input value. Now, I do want to make one last comment about a shift you're going to notice in the remainder of the course. From here on out, there's going to be much less of a focus on real-world applications in science, economics, business, and so on. But the math still has a purpose. It's just a different purpose, and a very important one at that. We're going to be justifying why everything we've been doing so far works, building up to eventually proving the fundamental theorem of calculus. So as you learn about how to calculate and interpret limits, keep that goal in mind, approaching a deeper understanding of calculus.